So in this video, we're going to look at finding a limit by using a theorem that's going to give us a shortcut method for finding a limit versus how we've been doing it in previous videos. Notice that I've called this theorem Theorem 3.2. So in the homework, you want to pay attention to when you're being told to use Theorem 3.1, which is the theorem we've been using in previous videos to analytically find limits, versus when you're allowed to use Theorem 3.2. So you need to pay careful attention in the homework to the instructions. So this theorem says that suppose we have a function f that is continuous over some open interval d. So continuous over an open interval d means I should be able to draw the function f without lifting my pencil from the paper over some open interval on the x-axis. So I have an open interval, call it d, on the x-axis, and a needs to be a number in that open interval over which my function f is continuous, has no discontinuities. And the theorem says that if I want to find the limit, as x goes to a of my function, as long as the function's continuous over an open interval at a, I can just plug a into the function and evaluate the function without having to use any of the tools that we were using in the previous video. So the idea is if I want to take the limit as x goes to a on my open interval over which my function's continuous, that means I'm going to be moving on the graph towards a point, and that point will have an input of a, and the output is just f of a. So and f of a is just going to be some real number on the y-axis. That's a horrible f of a. It's even bad for my poor penmanship, and I'm going to get the same thing again. So the theorem is saying, hey, as long as the function's continuous, the limit and the function value at a are going to be the same thing. So you don't need to do anything other than just plug a into the function to find the limit. So here's an example of the other comment would be, actually, before I dive into things, is really what this theorem is telling us. The key thing that's telling us is that if a limit isn't going to exist, it's going to not exist at a discontinuity. So places where limits won't exist will be places like this, perhaps where we have a piecewise defined function, where there's a break in the graph. This would be a place where the two one-sided limits don't exist. This happens at a discontinuity. I can't draw the graph without lifting my pencil. The limit could possibly not exist when I have the vertical asymptote at a value, where the function is going to infinity or perhaps negative infinity. So discontinuities in the graph are places where the limit won't exist. And so all this theorem is saying, as long as we aren't working at a spot where there's a discontinuity, we can just plug the value into the function to get the limit. So for example, these are functions that we worked with on the previous videos. When I look at this polynomial x squared minus 3x plus 2, we know that second degree polynomials, we know that their domain is x is an element of all real numbers. It goes from negative infinity to infinity. In other words, from pre-calculus, we know that we can plug in any real number we want into a polynomial. And clearly 3, the number at which I want to take the limit, 3 is an element of the open interval from negative infinity to infinity. And because the function x squared minus 3x plus 2 is defined for all real numbers, and 3 is a real number, to find the limit as x goes to 3 of my second degree polynomial, I can just plug 3 into it. So here I would say, hey, the limit as x goes to 3 of x squared minus 3x plus 2 is just going to be, and now I can drop the limit notation and just plug 3 into the function. 3 squared minus 3 times 3 plus 2 is 9 minus 9 is 0 plus 2 is 2, which is what we got in the previous video where we looked at this example using Theorem 3.1. So again, this second example here, I have a rational function. We can see that it's undefined when x is equal to 2. If we plug in 2, we get division by 0. So x cannot be 2, which means that the domain of this function is any x we want. We can plug in any value for x we want on the interval from negative infinity all the way up to 2. we have parentheses, union, we have to skip 2. We can't plug 2 in, so I don't use the square bracket here. I use the open bracket saying 2 is excluded, and then I can go from 2 to infinity. And then it says, hey, find the limit as x goes to 3 of this rational function. And then what I want to notice is that the open interval from 2 to infinity includes 3. In other words, 3 is an element of this open interval over which my function is continuous. So to find this limit, all I need to do is plug 3 into the function. I get 3 squared minus 3 times 3 plus 2 all over 3 minus 2, which is just equal to 2 over 1 is equal to 2, which is what we got in a previous video. The same function, however, x squared minus 3x plus 2 divided by x minus 2, if we want to take the limit as x goes to 2, because 2 isn't in the domain of the function, right? The x cannot be 2 because it causes a division by 0. 2 isn't in either of these open intervals, so we can't use theorem 3.2 to find this limit. We have to use theorem 3.1.